Hello, lovely students. So, this is the third part of our series on grade 9 circles chapter. This is chapter 5, basically, in our Ganita Manjari book for grade 9. So, in the first part, we learned about the basic concepts around circles, and we also started with Theorem 1. Then, in the second part, we covered from Theorem 2 to Theorem 7. This was all about chords in a circle. Now we'll come to Theorem 8. This is the last theorem on chord. And after that, we will start with another topic, which is arc. Okay, so let's start with this Theorem 8. So I'll start by drawing a circle. Okay, this circle has a center. I'll call this center C. Okay, then I'll draw a chord on this circle. I'll call this chord A, B, B. Okay, I'll draw another chord now. This chord is of length smaller than what we have for circle, uh, for chord smaller than chord AB. Okay, so let me call it C. C we have already taken, so this will be D, and let me call it E. Okay, so we have this DE. AB is a chord, DE is a chord. The length of DE is less than the length of AB. DE is shorter in length than AB. Now what I'll draw is, I want to see what is the distance between the center of the circle to the chord AB. Okay, so I drew a perpendicular line. We'll call this F. Okay, the point where this is joining the circle, the chord is F. Similarly, I will draw another perpendicular bisector from the center C to the chord DE. I'll name it as G. Okay, the place where it is intersecting the chord, I call it, that point, I call it G. So what have we been given so far? AB and DE are two chords of a circle with center C. Okay, CF is distance of chord AB from center. What else we are given? CG is distance of chord DE from center. We know all these things so far. What else I have told? I have told that the length of AB is greater than length of DE. This is the next thing that we know. Now, what do we need to prove here? What we need to prove here is the distance of the longer chord from the center is lesser than the distance of the shorter chord from the distance of the shorter chord. What we mean here is a longer chord will be at a less distance from the center. A shorter chord will be at more distance from the center, right? So here the distance of the longer chord from the center is CF. We are saying that this will be lesser than the distance of the shorter chord from the center. Shorter chord is DE. Distance of shorter chord from the center is CG. So CF is less than CG is what we need to prove. So let's get started on the proof. Okay. So what all we know so far? We know that CF is a perpendicular bisector of AB. Why? Because we have drawn a line CF. When we talk about the distance of a point from a line, we draw a perpendicular from that point to the line, right? So CF is perpendicular to AB, and from the earlier theorems that we have learned, we know that a line which is a perpendicular line drawn from the center of the circle to a chord bisects the chord. Okay, so this means AF is equal to BF is equal to half of AB, right? Similarly, we know DG is equal to EG is equal to half of D. Okay, these two things we know already. We also know AB is greater than DE, right? Now, what we can do is we can join the center to one of the endpoints of the chord. We do it for both the chords. Okay, so I have drawn a line joining the center of the circle to one endpoint, which is B of chord AB. Similarly, I have joined the center of the circle to an endpoint of the chord E of the chord DE. Okay, now what else do I know? When I joined it, what else do I know? BC is equal to EG. Why are they equal? Because they are both radii of the circle, right? Now what else? Can I close this? Okay. We know this. Now we also see, now we have seen, right, that this is perpendicular, this is perpendicular. So from this we can say that our triangles BFC and triangle EC or maybe EGC are right angled triangles, right? We can say this. These two triangles are right angle triangles. Now, in case of a right angle triangle, what we can apply? We can apply the Pythagoras theorem. What is a Pythagoras theorem? Why is this gravelly coming? Let me just get it done with once and for all. Yeah. Oh, still came. Okay, let's forget it. Let's continue. Okay, so these two are right angle triangles. Now we'll use the Pythagoras theorem on these two triangles. By Pythagoras theorem, what the Pythagoras theorem says is the square of hypotenuse is equal to the sum of the square of the other two sides, right? So let's first consider triangle BFC. BFC. Okay. Triangle BFC, our BC is the hypotenuse. So what we can say is BC square, okay, BC square will be equal to CF square plus, what is the other side? BF square, right? Now, we know already BF is half of AB. Okay, so we need to keep remembering it. Now we'll start with the other triangle. What is the other triangle? Other triangle is my triangle EGC. EGC. So in triangle EGC, what is the hypotenuse? Hypotenuse is EC. Okay, so we'll say our EC square will be equal to, EC square will be equal to CG square plus EG square. Okay, we have found this. BC square is equal to CF square plus BF square. Similarly, by Pythagoras theorem, EC square is equal to CG square plus EG square. Okay, now we already know that BC is equal to EC because they are both radii of the circle. Oh, here by mistake I have written G. It is C. Okay, they are radii of the circle. So what we can say is BC square will be equal to EC square. Right? BC is equal to EC. So BC square will be equal to EC square. Now BC square is CF square plus BF square. Let's replace it then. Say CF square plus what is it? BF square. So CF square plus BF square will be equal to CG square plus EG square. Right? EG square, CG square. Okay. Now what we can do is we know that BF is equal to half of AB. Or what we can say is, or AB is equal to twice of BF. Similarly, we can say EG is equal to half of DE, or DE is equal to twice of EG, right? Now we have been told, what we have been told, AB is greater than DE, right? So we can say half of AB will be greater than half of DE. Okay, so we need not actually consider this because the first part itself is enough to prove it. Okay, so AB is greater than DE, so half of AB will be greater than half of DE, right? Half of AB is BF and half of DE is EG. So we come to the conclusion BF is greater than EG. Also, we can say then in that case that BF square will be greater than EG square, right? Now, what we see here is, let's see, this is the one. Oh, sorry. This is the one we'll take now. CF square plus BF square is equal to CG square plus EG square. Now we are saying BF square is greater than EG square. To keep this balanced, to keep this equal, right? What is going to happen then? CF square will automatically be less than CG square. Or in other words, CF will be less than CG. Okay. Now this may be a bit confusing, so I'll just show with some numbers here. For example, we have to take the number 7. Okay, we take the number 7. Now I say that, for example, CF plus, I'm just here, no, I'm not squaring it, I'm just giving, taking the individual values, CG plus EG, okay? Or even if we are saying, we are taking the squares, it is fine. What I'm saying here is, I need to keep CF square plus BF square as 7. I need to find out two numbers, okay, where this sum is 7 and then this sum will also be 7. Okay, so what are such pairs? I can say 5 and 2, the sum is 7. Similarly, I can say 4 and 3, the sum is 7, right? So now what I see is, for example, we take these two combinations, okay, 5, 2 and 4, 3. Okay, now if I'm saying that CF or CF square is equal to equal to 5, right? And no, not CF square, basically BF square. Okay, and I'm saying that EG, BF is greater than EG. This we have already proved, right? So the other one, I'll take EG as, or basically EG square as 4, right? So now in this case, if I have to make, I have to add something to 5 to make it equal to 4 plus something, right? Here, what I have done is, the first term, I'm saying here that BF is greater than EG. So I have taken 5 is greater than 4. Now I have to find the second number so that both the sides are balanced, both have the sum 7, right? So if I have to keep it balanced, if I have to keep the end result same for both the sides, then what I need to see is that 5 is greater than 4. So here I'll have to add a smaller number. Okay, 4 is less than 5. To keep it equal to 5 plus something, I have to add a bigger number, right? So that is why if I have to make it equal to 7, I add a smaller number to 5 and a bigger number to 4. Okay, so this is the reason why we have said here, that BF square is greater than EG square, right? So the first term is greater than the first term of left hand side is greater than the first term of the right hand side. BF square is greater than EG square. So the second term, CF square, has to be less than CG square for the end result to be same on both the sides, end result to be equal on both the sides. Okay. That is why we have said that CF square has to be less than CG square. Because BF square is greater than EG square, CF square has to be less than CG square, and this means CF has to be less than CG, right? So this is proved. You can try, just like this example I have given with 5 and 2, two numbers 5 and 2, you can also try multiple examples on your own, right? So with this, we will write our theorem 8. How do we write the theorem? What have we been given? Here we need to talk in terms of the names of the chords and all. Otherwise, all these other theorems we have been writing generic. But here, because we have to specify, which chord is greater than which one, right? So we have to give the name of the chords. So we'll say let AB and DE be two chords of a circle with center C such that AB is greater than DE. Okay. Then in that case, then the distance from, let me wrap it up from here. Yeah. Then the distance from center C to AB will be less than the distance of center C from D. This is what we have proven, right? Okay. Based on this, what can we say about the diameter? Now that we know already, right, that diameter is also a chord. It is the longest chord of the circle, right? Now, what is the distance of diameter from the center? What is the distance of diameter from center of circle? You know already, diameter passes through the center of the circle, and that is why it is the longest chord, right? Now, if we are asking what is the distance of diameter from the center of the circle, it is already passing through that center of the circle. This means the distance is 0, right? And we say it is the longest chord of a circle, right? So can you see the relation? The longer the chord becomes, the shorter the distance from the center to that chord becomes, right? The longer the chord, the shorter is its distance from the center. Diameter is the longest chord, so its distance from the center is 0. Okay. And similarly, as we keep increasing the distance of the chord from the center, at one point, that chord will just be, the 2 points of the chord, they will just merge and, it will be becoming, it will overlap, it will become like a point on the circle, and its distance from the center will be the longest, which is the radius, right? Okay. So with this, we are done with all the theorems about the chord of a circle. So we'll come to the next topic now. We'll talk about arc. Now, what is an arc? What is an arc of a circle? You take 2 points. Okay. This is the center. Okay. And then I'll take a point here. And I'll take a point here. Okay. I'll call this point A. I'll call this point B. Okay. Okay. And this is the center. Oh. Now, the distance from A to B. Okay, this is called distance from A to B. In whatever way we travel, there are two ways of traveling from distance A to B. One is, what I'll say is, one is when I'm going from A to B this way, and another one is when I'm going from A to B this way, right? So to show that, I can just say that this is one way of going. I'll make a point here and I'll make another point here. I'll call this point X. I'll call this point Y. Okay. So an arc is two connected points on a circle. Okay. Arc is a connected portion of a circle. We have arc has two endpoints. Okay. And there is a curve connecting these two endpoints. Okay. I have shown you how we can go. One route going from A to B is through, you can say one route is A X B. The other route is A Y B, right? So the one which is covering a shorter distance, that is called the minor arc, and the one covering the longer distance is the major arc. Okay. So next what we'll understand is, I'll join this A to the center. I'll join this B to the center. Now what I see is it forms a angle AOB, right? So it forms an angle this. This is the angle AOB, and we call this angle as angle subtended by the arc AB. Okay, this is the angle subtended by the arc AB at the center of the circle. Okay, now what we'll see generally is, if this angle which is subtended by an arc at the center, if this angle is less than 180 degree, this is 180 degree. So it is less than 180 degree, then this arc is a minor arc. If this angle is greater than 180 degree, we will call this a major arc. What about when it is equal to 180 degree? Then there isn't a major or minor arc. 180 degree means a straight line, right? It will be a straight line. So this means it will be equal to 180 degree. It will be dividing the circle into two equal arcs. Okay, so this is about the basics of arc. Now this angle AOB, if I write angle AOB, right now I just marked it as, here to show you, right? But if I say angle AOB, there are two angles AOB, right? There is this angle and then there will be this angle, right? So there are two angles when I say angle AOB, there are two angles. So if the angle AOB is less than 180 degree, I am talking about the minor arc side. If the angle AOB is greater than 180 degree, I am talking about the angle subtended by the major arc at the center. Okay. Now, if I take a point here, I take a point here. This point is point C. Now this point C, okay, now here I'm talking about the arc AXB. AXB, okay. Now point C does not fall on this arc AXB. Where is the point C falling? Point C falls on the other side of the arc AXB. Okay, so this point C is not falling on this arc, it is falling on the other side of this arc, which is AYB, right? So now the angle which is subtended, now for example, if I join this and I join this, then this angle is called, what is this angle called? This will be the angle subtended by arc at a point on the circle at the other side of the arc, because it is a point on the circle, but it is on the other side of the arc. Or we can say it is a point on the circle, but outside the arc. Okay, we can also say it is a angle subtended by the arc at a point on the circle which is outside the arc. So with that, we will come to the next theorem. This is the first theorem on the arcs. So we will have a center. We call this center O. Then we will have point. We define 2 points on the circle. Point A, point B. And what I'll say is I'll make another point here. This is the point F. I'll make a point on the other side. This is the point. We'll call it point D. Okay. So here AFB is the arc. Okay. What else? ACB is the angle. Sorry, it's defined. It's not C. I have defined the center of the circle as O. Okay, so far we have been calling it. Okay, so angle OAB is the angle subtended by the arc at the center of the circle. Okay, now we have taken D is a point on the circle outside of the arc AFB, right? Now what we'll do is we'll join the center of the circle with this point D. Okay, I'll delete this one. Okay, so I have joined the center of the circle with this point D. And what else I'll do is I will extend this line OD. I'll extend this line and let it cut at a point. Now it is cutting it exactly F here. So I'll just shift the point F to this. I'll say this is F. Or maybe I'll just make a bigger point here. This is F. Okay. Now I'll extend it so that it is cutting. It is intersecting the circle. So OD is extended so that on the other side, so that it cuts the arc AB at some point, and this some point I'll call it as, I'll name it as E. Okay. So this is our point E. Okay. Now we have extended that. Now what I'll do is I'll join OB and I'll also join OA, right? Now what I need to prove here is D is a point on the circle outside of the arc AFB. The line OD is the line joining the center of the circle to point D. OD is extended and it intersects the circle at E. Okay. Now these all are given. What we have to prove here is that the angle subtended by this arc, the angle subtended by this arc at the center is twice the angle subtended by this arc at any point on the other side of the arc. So what I'll do is I will join AD. I'll join BC. Sorry, DB. Okay. And now what we have to prove here is this is the angle, right? So what we have to prove here is we have to prove here is that angle AOB is equal to angle AD twice of angle ADB. What I need to prove is this angle is twice of this angle, right? So what we are saying is the angle subtended by an arc AFB at the center of the circle is twice the angle subtended by this arc at any point, any other point on the circle which is outside of this arc. Okay, this is what we need to prove. So let's get started. Now here what we see is we see two triangles AOD and we see a triangle BOD. Okay, let's first consider the triangle AOD. Okay, so we have triangle AOD. Okay, in triangle AOD, OA is equal to OD because they both are radii of the circle, right? So this triangle AOD is an isosceles triangle. This AOD is a isosceles triangle. So what does that mean? That will mean that this angle will be equal to this angle, right? So what we are basically saying here is OAD is equal to ODA. This is one angle, this is the other angle. These two angles will be equal. Now, what we see is this angle AOE. This angle AOE is the exterior angle of the triangle. So what I'll do is I'll just copy it and erase a few things so that we get more clarity. Copy this, paste it here. What I'll do is I'll just keep this portion for now. I'll remove these things. Okay, I'll even remove this. Okay, and I'll remove this. So this is a cleaner figure, right? Here we can very clearly say, see, OA, OD are the two radius of the circle, and because this triangle OAD has two sides equal, it forms a isosceles triangle. The opposite angles of the angles which are opposite to equal sides are equal in an isosceles triangle. So this means angle OAD will be equal to angle ODA. So this is clear until now. Another point that we will see here is this angle. Now this angle is the exterior angle of the triangle. Angle AOE is the exterior angle of the triangle. So we know the property of the property of a triangle, that the exterior angle of a triangle is equal to sum of the opposite interior angles. So when I'm saying this, what this means is angle AOE will be the sum of OAD and ODA, right? Not able to write. Okay. Now what we'll say is, let's call this let's call this 1. Okay. Now what we'll consider is the other triangle now. Okay. So what I'll do is, no, it's not copying. Something has seriously gone wrong. So what I'll do is, I'll just take the eraser, erase all this. Okay, clean it up. Now I'll again copy this. What we'll do here is, now I'll just remove this side of the triangle. Now, some reason my keys are not working properly. Okay. Okay. Remove this, remove this, remove this, remove this. So now it has just what we needed. Okay. So it is the same figure in the first one. For the sake of clarity, we removed other things. Okay. So that we could only see AOD triangle and the line DE. Right. Now we have cleared the other side. So we only see the triangle DOB and the line DE. Now here we will talk about triangle ODB. Okay, we'll talk about this triangle. So what about this triangle? Here again we see the same thing. OD is equal to OB. Both are radius of the circle. That is why they are equal. So this means triangle ODB is an isosceles triangle. Okay, it is an isosceles triangle. So because it is an isosceles triangle, angles opposite to the equal sides in isosceles triangle are equal. This makes our angle ODB and angle OBD equal. So this angle is equal to this angle, right? Now what we see here, about this angle. Angle EOB or BOE. So BOE is the exterior angle, the triangle. Angle BOE is the exterior angle of the triangle. So what we can say here, okay, what will do here is and copy, because it is the same property here. Exterior angle of a triangle is sum of opposite interior angles. So angle BOE will be the sum of ODB plus OBD. And I'll say this is the second one. Okay. Now let's now go back again to this complete figure. Copy this. Okay, now what I had to prove here was angle AOB is equal to angle twice of angle ADB. So let's start with proving that. Now what I'll say here is angle AOB. What is it made by? It is made by two angles, right? What two angles is it made by? Between this angle and this angle, right? Similarly, what is angle ADB made of? This angle and this angle. Okay, I'll remove the other unnecessary parts. Okay, so angle AOB is the sum of angle AOE plus angle BOE. Okay. So what we have seen is angle AOE is equal to OAD plus ODA. Okay. What is OAD and ODA? This is OAD, ODA, right? So we can also say from here that it is angle AOE is equal to twice of ODA, right? Can you see that? OAD and ODA are equal. So we can write this as ODA plus ODA, which makes it 2 of ODA, right? Similarly, here we can also say that BOE is equal to twice of ODA. BOE is twice of ODB because OBD is equal to OBD is equal to ODB. So we can write ODB plus ODB, which makes it twice of ODB. So now we are saying AOB is the summation of AOE and BOE. Okay, so what does that mean? So we'll write again AOB is equal to AOE, which is twice of ODA, twice of ODA. BOE is twice of ODB. We can say angle, right? Where from did we get this? We got it from this one and got it from this one. So we took these two things and replaced. Okay, now let's see what is ODA. ODA is this part and ODB is this angle. So we can write this is equal to, we can take 2 out and we'll say ODA plus B. This is the angle. Okay. Which means it is twice of, what is the sum of ODA plus ODB? This is ODA and this is ODB. The sum is ADB, right? So this is twice of ADB. So we have proved here AOB is equal to twice of ADB. So we'll say hence proved. Okay, and now we can write our theorem 9 with this. So, but before we write the theorem 9, okay, there is one more case. What is the case here? What we have done here, when I have D is, excuse the noise, please. There are some kids playing outside, so that is why a lot of noise. Now this point D, okay, it is at such a position that when I am extending it to DE, okay, this point E falls on the arc AFB. It falls on this arc, right? There can be another case where if I extend this line OD, it may not fall on the arc AFB. It may fall on an arc on the on outside of this arc. How this can happen? Let me draw a circle. Okay, now I'll draw. Okay, let me first put a center. Okay, and we have 2 points A, B, and I have a point F, which is somewhere between A and B. Let me make the arc. So I'll join it to the center. I'll join this point B to the center. And this is, I'll call this point O. O is my center. Okay. Now I'll take another point D on the circle. Now here I have taken D at this point. Okay. Now what I'll do is I'll join A to D. See here? And I'll join B to D. Okay, so what is happening here? This AOB is the angle subtended by this arc AFB. D is a point on the circle outside of the arc AFB. The angle subtended by this point, this is ADB. Okay, so ADB is the angle subtended by the arc at a point which is outside of this arc. Now what we had done here is, in this 1. The first case, what we had done was we had joined O to D. So here also I will join O to D. OD is the radius, right? Because D is at a point on the circle. So any point on the circle, when I join with the center, it forms the radius. So that is fine. Now, what we had done was, in the earlier case, what we had done was, we had extended this line OD so that it intersects the circle. Now, when I am extending it, see, it will intersect the circle here. Let me call this point E. Okay. So you see here the case that E is not falling on the arc AFP. E is also falling at a point on the other side of the arc. Now, how do we prove in this case? So here also what we have to prove is the angle subtended by the arc at the center is AOB. So this is our angle AOB. What I have to prove is it is twice of the angle subtended by the arc at a point on other side of the arc or outside the arc. So that angle is ADB. 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 We have to prove this. So let's start now. So how do we start? Now here what I should do is I'll copy this circle, this entire diagram, and just like we did earlier, I'll remove the extra parts so that we see one triangle at a time. Okay. So what I'll do here is I'll just consider the triangle AOD or ADO. Okay. So I will remove this, I will remove this, I will remove this, and I'll remove this. Okay. So we have this triangle only. Now what I know about this triangle, one is I know that OA is equal to OD. Why is it equal? Both are radii of the circle. Now what this makes triangle AOD, it becomes a isosceles triangle. Became isosceles triangle. So this means, what this means is the angles which are opposite to the equal sides are equal. So OAD will be equal to ODA. Okay, both are equal. Now I'll see this angle. This angle AOE, this is the exterior angle of the triangle, right? AOE is exterior angle of the triangle, and it will be the sum of interior opposite angles. So what will it the sum? It will be sum of OAD plus ODA. Okay, this is equal to AOE. Now what I can also say is OAD is equal to ODA. So I can write it as ODA plus ODA, which makes it twice of ODA. Twice of angle ODA is equal to angle AOE. Twice of angle ODA is equal to AOE. Okay. Now this is our first one. Okay. Now I'll take this diagram again, copy it, and keep only the second circle. Sorry, second. What happened? This is the diagram. I do a copy and I do a paste. And I'll move it here. Now, first time I took this circle. So this time I'll remove this circle. Okay, and I'll just keep this circle. Sorry. Oh my God, what I'm saying. In this one, I kept this triangle. So in this one, I removed this triangle and I just left the other triangle. Now I'll start seeing what I know about this triangle. This triangle is BOD. So what do I know about this triangle? I know OB is equal to OD. Why? Because both are radius of the same circle. Now this means BOD is an isosceles triangle, which means angle ODB is equal to angle OBD. Said this is a isosceles triangle. This angle is equal to this angle. So let me make these angles. This angle, this angle. Now what about this angle? Right? We see here that angle BOE is equal to angle ODB plus angle OBD. Why? Because this is the exterior angle is the sum of opposite interior angles in a triangle. We already wrote that and understood that multiple times. So we can say that this is twice of ODB. Why this is twice? This is ODB plus OBD. OBD and ODB are equal. So we can say ODB plus ODB, which makes it twice of OBD. So we are saying angle BOE is twice of angle ODB. And I'll say this is 2. Okay. Now I'll take this diagram once more. I'll copy it down. And now we'll just see what we need to find. So what we needed to find is angle AOB and angle ADB, right? Now, if I consider angle AOB in terms of angle AOE, right? Because here I know about angle AOE. I know about angle BOE, right? So, what can I say? If I see angle AOE, it is the sum of angle AOB plus angle BOE, right? AOE is the sum of angle AOB and BOE. See here, this is AOB, this is BOE, and this is our entire angle AOE. right? So this angle AOE is the sum of AOB and BOE. So what I know about AOE, AOE is twice of ODA. Or maybe I can write it like AOB is equal to angle AOE minus angle BOE, right? You can write like this also, that AOB is angle AOB is equal to AOE minus BOE. Now what do I know about AOE? It is twice of ODA. Twice of ODA minus twice of BOE is ODB. Right? I can take 2 outside and then I will say ODA minus ODB. Okay, now let's see what is angle ODA. ODA. ODA is this angle. Okay, this angle, and I am subtracting ODB from it. ODB is ODB. So from this big angle, if I am subtracting this small angle, what does it give me? It gives me this angle, right? So this means I can say equal to twice of angle ADB. The small angle is ADB, right? Right? So if I write it here again, AOB angle is equal to twice of ADB angle. AOB is the angle subtended by arc AB at the center. ADB is the angle subtended by the arc at a point D on the circle, which is outside of the arc AFB. So this means this is the same thing. This is the same thing which we proved earlier, right? This, in the first case also, we had proved this. And in the second case also, where E is not falling on the arc, but it is outside of the arc, there also we have been able to prove this case, right? So now we are in a good position to write our theorem 8. It's theorem 8, right? No, it's theorem 9, I guess. Let me check in the book what is the theorem number. Yeah, this is the theorem 9. So theorem 9 is the angle subtended by an arc at the center of the circle is twice the angle subtended by that arc at a point on the circle which is outside of the arc. Okay. Yeah. So we have proved this. So what this means is you have a circle here. You have 2 points here, A, B. This is the, where is, yeah, this is my center of the circle. Okay, and then what we mean here is, this is the angle made by the arc at the center. Okay, now you can take any point on the circle which is outside of it, whether it is this point, whether it is this point, whether it is this point, or it is this point. Okay, any point. You can take this point, this point, this point, this point. Any point on this circle you can take. Whatever point you take, if you're joining this, the endpoints of the arc to this point, the angle made will always be half of what it made at the center. So, for example, this point is C, this point is D, this point is E, this point is F. Okay. So what I say is, let me join. I join it to D. Now I can join it to AE. I join it to F. So what I am trying to say here is, the angle which is subtended by this at the center is this. Let me name the center also. The center is O. Okay. So AOB is the angle made by this arc at the center. So what we mean to say here is that all these angles, ACB, ADB, AEB, AFB, all these angles, they are half of AOB. What this means, what can we deduce from it is, ACB will be equal to ADB, will be equal to AEB, will be equal to ABF. All these angles will be equal. Okay, so this is what we can deduce from it. Another thing which we can deduce from it is, what about, okay, let me make another circle here. Okay, and let me show the center. Let me call this center as O. Okay, now this is my point A, this is my point B, and this is actually the diameter. Now this points A and B, the arc that they are making, okay, this is basically, they are dividing this circle into two equal parts, because this is the center, they are passing through the center of the circle. So here AB is diameter of the circle. I will define a point here. I'll call this point F. To make a point here, F. Okay. So what I want to prove now here is this angle, okay, which is made by this arc AFB at the center of the circle is, okay, what I want to prove is, I'll take a point on the other side. Okay, I'll call it D. So what I want to prove now here is, sorry, what I want to prove here is the angle which is subtended by this arc at a point which is on other side of the arc. So AB is the diameter of the circle, AFB is the arc of the circle, D is a point on other side of the arc. Okay, so what we need to prove is to prove ADB is equal to 90 degree. What we need to prove is ADB is equal to 90 degree. How do we prove it? Now the angle subtended by the arc AFB at the center is angle AOB, right? Angle AOB is 180 degree, right? Because it is the diameter, it is passing through the center of the circle. So it is 180 degree. Now the angle subtended by this arc at a point on the other side of the arc will be half of what it subtends at the center. So with that theorem, angle ADB will be half of angle AOB, which means ADB will be half of 180 degree, which is 90 degree. 90 degree. Proved, right? So we covered the portion of the arc. It was a long one because we had to go through each and everything separately to understand it better. It took more time than what the theorems took in the previous video. So to understand each of them clearly, just write it down in the notebook as you are watching, make the diagrams, and as I am explaining, you also keep writing it in your notebook so that you are able to pick it up better. And in case you have any questions, you can drop me a comment and I'll respond back to you. Okay, with this, I'll close this and I'll see you in the next video, which will be last part of our series on grade 9, chapter 5, circles. Bye-bye.